This is my lab 4 on Faraday's Law by Elias Grimon. The contents of this lab include the introduction, which are the purpose and the experiment, the measurements, which are the data and calculations, and the closed grip model. The experiment in this lab states that the time data of a magnet falling through an aluminum tube will be collected to help understand Faraday's Law and develop a computational model to visualize the law in action. The formulas used in this lab are Faraday's Law, which states that the electromagnetic force is the result of the change in magnetic flux over the change in time. Additionally, the Biot-Savart law from Lab 2 was used. The results of this lab are that the real-life experiment took about 1.21 seconds for the magnet to fall through the tube, and the glow script model stated that it will take 1.168 seconds. The experimental design of this lab is that a bar magnet will start at the top of a non-ferrous conductive tube. The timer is started when the bar magnet is dropped and finished when the bar comes out of the bottom. Faraday's law states that the opposing magnetic field, which is created by an induced current, will slow the velocity of the bar magnet for a certain instant of time during the descent. The measurements in this lab were that the metal tube was 0.3 meters, the width was 0.006 meters, the inner radius was 0.02, and the radius was 0.032 meters. The mu for the magnet from lab 2 was 5, and the mass of the magnet was 0.025 kilograms, and the average time it took for the magnet to fall through the tube was 1.21 seconds. For the glow script model, the measurements of the tube were inserted in the magnet measurements for the initial conditions. The code for the functions of this lab were the magnetic field calculation and the magnetic flux calculation. Additionally, the induced current was calculated, and the magnetic force on each ring of the tube was calculated. Then the net force was calculated by calculating the magnetic force on the magnet in the opposing direction, and then the gravitational force that was pulling it down. The position and velocity of this bar magnet was plotted, and this will be shown later in the video. So this is the visual model. It can be seen as the bar magnet was falling through the tube. The blue represents the opposing magnetic force, and the red is the falling magnet, the gravitational force. This magnetic force arises from the induced current of the moving magnet through the tube. So the graph states that the velocity increases up to a certain point, but the opposing magnetic force slows it down and keeps it constant until the tube is no longer there and the bar magnet accelerates once again. It states that the time in the tube would take about 1.168 seconds. So for the discussion, if the conductor had near zero resistivity, the induced current would be very large, according to Ohm's law. This means that it would take the magnet a longer time to fall through the tube. If there were holes or slots in the tube, there would have been a reduced induced current and lower magnetic force. This would make the bar magnet fall through the tube faster because there was less induced current. Lastly, a non-ferrous tube was needed so that it would not interfere with the bar magnet falling. Aluminum would not have stuck to the bar magnet, and that is why it was used. The results of this lab were that it would take 1.21 seconds for the bar magnet to fall through in real life, and in the glow script model it took 1.168 seconds. The mu value could have been a possible source of error and needed to be altered because it was from lab 2. It was 2 amperes times meter squared, but this didn't work according to the data, and I changed it to 5. Additionally, this lab was useful in studying Faraday's law and testing it experimentally and computationally in developing a deeper understanding of the law. And other laws that were used included the Biot-Savart law and the